back to Math 143, Finite Mathematics. In our previous lecture, we studied the multiplication principle. We learned that when a process has several stages, we multiply the number of choices at each stage to find the total number of possible outcomes. Today, we will study two closely related counting methods. The first one is permutation and the second one is combination. Permutations and combinations. The main question we will ask throughout this lecture is, does order matter? If order matters, we use permutations. If order does not matter, we use combinations. So, by the end of today's lecture, you should be able to evaluate factorial expressions, calculate permutations involving repeated objects, calculate combinations, and determine whether a problem requires a permutation or a combination. Okay, before introducing the permutations and combinations, we need to understand factorial notation. What is the factorial means? The factorial for a positive counting number n can be any value, the counting number 1, 2, 3, 4 up to infinity. The factorial n, we use the exclamation mark as represent the factorial. The exclamation mark is read as factorial. Therefore, the factorial n is the product of all values starting from n times n minus 1, n minus 2 up to 1. Let's see the example. For example, factorial 5. 5 factorial. So here n equals 5, then 5 factorial means n times n minus 1 times up to 1, 5 times 5 minus 1, 5 minus 2, 5 minus 3, like this. Therefore, 5 times, 4 times, 3 times, 2 times 1. So the 5 factorial or factorial 5 equals 120. 120. Similarly, let's see one more example. Three factorial, the product of all the values until 1, 3 times, 2 times 1, 6. Right? The product of all values up to n, right? So here is the important thing. By definition, 0 factorial or factorial 0 always equal 1. The value 0 factorial equals 1 may seem unusual, but it is necessary for permutations and combinations formulas to work correctly. Okay, let's go for the quick practice. What is 4 factorial? Pause the video and try it by yourself. 4 factorial, 4 times, 3 times, 2 times, 1, 4 factorial, 24. Then what about 6 factorial over 4 factorial. So 6 factorial, we can expand this 6 factorial as 6 times, 5 times, 4 times, 3 times, 2 times 1, and 4 factorial, 4 times, 3 times, 2 times 1. Finally, we have this cancellation, 6 times 5, 30. We often simplify factorial expressions by cancelling rather than evaluating very large factorials. Right? Again, we often simplify factorial expressions by cancelling rather than evaluating very large factorials. Okay, then let's go for the permutations. Permutations. So a permutation is an ordered arrangement. Simply, we can say a permutation is an ordered arrangement. An ordered arrangement of R, think about an ordered arrangement of R distinct objects. We selected from n distinct objects. So here we have n distinct objects. We select R distinct objects. So, an ordered arrangement of R distinct objects selected from n distinct objects is called a permutation. Again, for permutations, the order matters. So let's see the formula. The formula is we use P to represent the permutation. Out of n distinct objects, select R, then n factorial over n minus R factorial. The essential idea is order matters. Right? Okay. Let's say the example. How many ways can 3 students be selected and ordered from a group of 5 students? How many ways can 3 students be selected and ordered from a group of 5 students? Okay. Notice that we are not simply choosing 3 students. We are also arranging or ranking them. For example, again, notice not simply choosing 3 students. We are arranging or ranking them. Okay, then let for example Alice, Ben and Carlos is a different ordering form. Also, Carlos, Alice and Ben, two different ordering forms. Therefore, order matters and we use permutations. Two different orders. Therefore, order matters and we use a permutation. So select 3 out of 5. 5 factorial over 5 minus 3 factorial. That is 5 factorial over 2 factorial. 5 times, 4 times, 3 times 2 factorial over 2 factorial. Final answer is 60. Therefore, 60 ordered selections are possible. Okay, then let's interpret the permutation. So let's say permutation 4, 4. N equals 4 and R equals 4. Also, P out of 4, select 2. Okay, first, let's say P for 4, that is 4 factorial, 4 minus 4 factorial. 4 factorial over 0 factorial. So we know that the 0 factorial means 1, therefore 4 factorial. 24, 4 times, 3 times, 2 times 1. This means all 4 objects can be arranged in 24 different orders. This means all 4 objects can be arranged in 24 different orders. Okay, then let's move forward. P for 2. Then 4 factorial over 4 minus 2 factorial. 4 factorial over 2 factorial. 4 times, 3 times 2 factorial. 2 factorial. 12. This means 2 ordered positions can be filled from 4 distinct objects in 12 ways. So this means 2 ordered positions can be filled from 4 distinct objects in 12 ways. Right? Okay, let's use the tree diagram. Suppose we have 4 objects. Suppose we have 4 objects A, B, C, D, and we arrange 2 at a time. Okay, let's see. For the first position, there are 4 choices, right? So, first position, second position, right? Okay, for the first position, there are 4 choices. And after choosing one object, there are 3 choices remaining for the second position. Three choices. Therefore, 4 times 3, 12. Therefore, 4 times 3, 12. The outcomes include, let's say we have AB, AC, AD, also BA, BZ, BD, and so on. Notice that AB does not equal BA. That confirms that order matters. Right? Okay. Let's go for the one more example. There are 6 runners in a race. How many ways can first, second, and third place be awarded? Okay, think about the first place, second place, and third place are different positions. Therefore, order matters, right? So, first, second, and third. Places are different positions. Therefore, order matters. Permutation out of 6 distinct objects. Select 3. 6 over 3. 6 times 5 times 4 times 3. 3. Therefore, there are 120 different finishing orders are possible. Right? So, let's go for the additional permutation examples before moving into the combinations. Example, how many ways can 11 people be seated in 11 seats? How many ways can 11 people be seated in 11 seats? Every person is being arranged, therefore 11 factorial. So every person is being arranged, therefore 11 factorial. Seating changes when people exchange positions, so order matters. The first, second, third up to 11 positions. The first seat we have 11 options, second one we have 10 options, third one we have 9 options up to 11. So seating changes when people exchange positions, and that means it confirms the order matters. Okay, then a disc jockey has 13 songs available and chooses 7 songs to play in order. Because the order of songs matter, how many ways that we can select 7 from 13? So P choose 7, select 7 out of 13 distinct. 13, 6. You can simplify the answer. One more example. You rank the 3 best movies from 20 movies. You rank the 3 best movies. Since first, second and third places are different, since first, second and third places are different, permutation, select 3 out of 20. 20 factorial over 20 minus 3 factorial. Simplify the answer. Okay. So far, every object has been distinct. Then, but what happens when some objects are identical? Okay, let's see the permutations with repeated objects then. Okay, suppose a collection contains n objects total with repeated groups of sizes n1, n2 up to nk. That means the sum of all n1, n2 up to nk equals n. Suppose a collection contain n objects with repeated groups of sizes n1, n2 up to nk. Then the number of distinct arrangements is n factorial over n1 factorial times n2 factorial times up to nk factorial. So we divide because interchange in identical objects does not create a new arrangement. Right? Okay, let's see the example. Think about word statistic. Example. How many distinct arrangements can be made from the letters in the word statistic? How many distinct arrangements can be made from the letters in the word statistics. Okay, first count the letters. First count the letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Statistic has 10 letters. So count repetitions then. So we have S appears 3 times. T appears 3 times. I appears 2 times. A appears once. C appears once. Therefore, 10 factorial over 3 factorial times 3 factorial times 2 factorial times 1 factorial times 1 factorial. Then calculate. We know that we can simplify this. 10 factorial, 3 factorial times 3 factorial times 2 factorial. Use your calculators. 50,400 distinct arrangements are possible. Right? Okay, next example. The word balloon. How many distinct arrangements? The word balloon has 7 letters. Repeated letters. L appears twice. O appears twice. B, A, and N appears only once. Therefore, how many distinct arrangements? 7 factorial over 2 factorial times 2 factorial. 1260 distinct arrangements are possible. Okay, I will give you the practice example. So practice the word level. Okay. Okay, now let's discuss the combinations then. So again, permutations, order matters, combinations, order does not matters. Combinations. A combination is an unordered selection. Simply, we can say a combination is an unordered selection. The formula is C n choose R. So we use n choose R in factorial over R factorial times n minus R factorial. The essential idea is order does not matter. The essential idea is order does not matter. Okay, let's see the example. How many ways can 3 students be selected from a group of 5 without regard to order? Example, how many ways can 3 students be selected from a group of 5 without regard to order? This time we have again Alice, Ben and Carlos, the same group. Then think about Alice, Ben and Carlos. So this is the same group as Carlos, Ben and Alice. Therefore, order does not matter. Use a combination. Choose 3 out of 5. 5 factorial over 3 factorial, 5 minus 3 factorial. 5 factorial over 3 factorial times 2 factorial. Simplify the answer. So answer should be 10. Therefore, 10 groups are possible. When order matters, there were 60 possible selections. When order does not matters, only 10 possible selections. Okay, let's see one more example. A committee of 4 people is selected from a group of 10. Because there are no assigned positions, order does not matter, then choose 4 out of 10 combinations, 10 factorial, 4 factorial, 10 minus 4 factorial, simplified 10 factorial, 4 factorial over 6 factorial, 210. Therefore, there are 210 different committees are possible. Okay, then before using a formula, ask whether changing the order creates a new outcome or not, because we wanted to identify either the permutations or combinations. Okay, let's see. Permutation or combination. First, before using a formula, check whether changing the order creates a new outcome or not. So, for an example, assigning ranks, order matters. Use permutations. Forming a team, order does not matter, use a combination. Seat in people, order matters, then use permutation. Selecting lottery numbers, order usually does not matter, use combinations. Okay, let's say comparison example. Suppose 3 students are selected from 10 students. Okay, comparison example. Suppose 3 students are selected from 10 students. Case 1, forming a study group. A group has no position, right? So, forming a study group. So, that means a group has no positions. Use combinations. C. Choose 3 out of 10. Case 2. Selecting president, vice president and treasurer. Selecting president, vice president and treasurer. These are different positions, so use permutations. Permutation, select 3 out of 10. The same 3 people assigned to different officers produce different outcomes. Okay, let me give you the practice problems. Practice problems. First one. How many ways can 4 books be arranged on a shelf? How many ways can 4 books be arranged on a shelf? All 4 books are arranged, so 4 factorial. Practice number 2. How many ways can a president and secretary be selected from 8 people? So positions are different. Use permutation. Okay, practice number 3. How many ways can 3 cards be selected from a standard 52 card deck? How many ways can 3 cards be selected from a standard 52 card deck? Order does not matter, use combinations. Practice question number 4. From 12 students, how many groups of 5 can be selected? Okay, pause the video and try it by yourself. Okay, what are the common mistakes? Let's review the most common mistakes. Using a permutation when order does not matter. Using combinations when positions are different. Forgetting that 0 factorial equals 1. Evaluating larger factorials unnecessarily instead of cancelling. Forgetting to divide by repeated factorials when objects are identical. Counting repeated arrangements are different. Assuming word like choose always mean combination. Sometimes the choices are ranked or assigned positions. Those are the common mistakes. Then I will give you the quick decision strategy. Use this 3-step approach, right? Okay, very important then. Step 1. Are objects being arranged, ranked, seated, or assigned positions? If yes, use permutations. Are objects being arranged, ranked, seated, or assigned positions? If yes, use permutations. Is a group being selected with no special positions? Use combinations. Step 3. Are some objects identical? If yes, use the repeated object permutation formula. Okay, let's summarize today's lesson. We first introduced factorial notation. Then we studied permutations where order matters. We also learned how to count distinct arrangements when some objects are repeated. Finally, we studied combinations where order does not matter. The most important question is, does change in the order creates a different result? If yes, use permutation. If no, use combination. These counting techniques will be extremely useful when we begin probability in our chapter 7 because probability often requires us to count both the total possible outcomes and the favorable outcomes. Okay, thank you for watching. and I'll see you in the next lecture.